Welcome back to Codex. Our speaker today is Soledad Villar, who is an assistant professor in the Department of Applied Mathematics and Statistics at Johns Hopkins University. Professor Villar received her PhD from the University of Texas in 2017 under the direction of Rachel Ward, and then spent 3 years as a postdoc at NYU before joining the faculty at Johns Hopkins. Soledad is known for using tools from optimization to tackle emerging problems in machine learning and data science. Today, she'll tell us about equivariant machine learning. Take it away, Soledad.
Thank you for the invitation and for the introduction. So this is me, Soledad. I'm going to talk about equivariant machine learning. Please ask questions if you want to discuss or if you have questions. And I have a lot of material, but I don't have to cover it all. So we can discuss whatever things you think are more interesting. So this talk is about equivariant machine learning, and especially it's about symmetries. And symmetries are very powerful in many applications. In particular, I may argue that symmetries are powerful in deep learning. Deep learning has very large models that are very well parameterized, but there is some structure to them. It's not just anything. And some of this structure is said to exploit the symmetries, either in data or in problems, or both. So for instance, convolutional neural networks implemented some convolution and symmetry that has to do with being like if you have a classifier or like if you're learning features, they are invariant or with respect to small translations or rotations or deformations of your images, so that by applying the same convolution filters at different locations of images, say. Recurrent neural networks also exploit some sort of symmetry that had to do with the time translation symmetry by applying the same recurrent units at different locations of text. And graph neural networks, which is something that I thought about for a long time, also have some symmetries, which is like the functions that you learn are invariant with respect to relabeling of the nodes, or if you have a graph and you write this as an adjacency matrix, then these graph neural networks that you learn need to be equivariant or invariant with respect to permutations of rows and columns. So the action of permutations by conjugation in these matrices. So one way to implement that symmetry is by doing message passing algorithms, which is every node has some features, and it sends messages to their neighbors, and the neighbors aggregate. That, of course, is independent of how you represent that graph as an adjacency matrix, and therefore it has the symmetry that we care about. I'm going to discuss different ways that one can implement symmetric functions and how can you exploit it in neural networks or in machine learning, and how much can you gain in some way of measuring it when you implement these symmetries. So I'm going to start with the definition of this exact symmetry. So I guess that's something to mention, is that the first symmetries that I mentioned at the beginning, like time translation and convolution symmetries, is some kind of like an heuristic interpretation of what's going on. But here in this case, I'm going to talk about exact symmetries, exact implementation of symmetries in the class of functions that we care about. So we are going to consider G, a group, is going to act on some data set that lives in Euclidean space, like in RD. And then F is going to be an invariant function if when you apply it to a point X and you apply it to and you take a group element and you multiply G times X, then F of G times X is equal to F of X for all G and all X. That's invariant. And then if G also acts in the range of the function, then you can define equivariant, so that if you act in your input, then you act on the output by the same group element. So you don't need to have the same action in both spaces, but you just need to have the same group acting in both spaces. So for example, if I have this graph, I can write it as this adjacency matrix or this adjacency matrix. The change from here to here is just an action by permutations, like that is conjugation. And then, so for instance, if I ask a function, what is the length of the shortest path that visits every node, then that function is invariant. It doesn't matter whether you give it this or that. So it satisfies that f of the action on A is equal to f of A. And if you give it, if you ask what is the shortest path and you ask it as a sequence of nodes, then that function, you can think of it as an equivariant function in the sense that if I act on the input, then I act on the output by the same permutation, like just the permutation of the nodes. Okay, so another data science algorithm that is also equivariant with respect to these permutations is the spectral methods. Like if you take a graph and you look at the top eigenvectors, say these, then if you do these permutations of the rows and the columns, then the eigenvectors have the same permutation. And this is the reason why one can do spectral clustering, for instance. And this suggests a different way to define a graph neural network. So instead of doing message passing, one can do some form of generalization of spectral methods and then obtain the same kind of result that we want, which is basically like say your graph neural network learns an embedding for every node in RD, and you want that if you do a permutation on the labels of the nodes, then the embedding that you learn is permuted accordingly. So spectral clustering also has that property. And you can parameterize a space of functions that have that property by, say, learning a way of combining operators associated to the graph with, say, you can consider some form of regularized Laplacian, or like a linear combination of these operators that are associated to the graph, and then think of a neural network as learning how to combine the operators of the graph and just learning some form of a spectral method. The actual definition from the paper by Chen, Li, and Bruna, that they use it for community detection, is inspired on these like non-backtracking walks that people use for like clustering the stochastic block model. They have a specific graph Laplacian that they show, find the correct communities, and they just parameterize a class of functions where those like regularized Laplacians are a specific point. I don't need to go to the details of this, but just so I show you like some connection between equivariance and spectral methods and graph neural networks, just like these things are connected. I think that my main point of my talk today is regarding other forms of symmetries, not necessarily permutations, symmetries, and graph neural networks. These are things that I've been working in the past year, like other forms of symmetries, and in particular the symmetries from physics. So the laws of physics impose symmetries and impose constraints that just like, because physical law satisfies many symmetries. So if we want to say learn a physical system, one may say that we may need to encode the rules of physics in that system so that the learning has the right model, uses the right model, and therefore it produces better generalization. One particular case of that philosophy is what is called the physics-informed machine learning. Karniadakis has a survey of different methods that people use, which is basically just use neural network. Like if you want to use machine learning for physics or like, I don't know, fluid simulations or whatever, you can just, you should not like forget everything that you learned from applied math in the past 30 years. You can incorporate these as modules in your learning, and that would make it like you can do machine learning and also use classical numerical methods by incorporating these two things. So the classical example is this machine learning methods that incorporate like numerical integrators, for instance. Like if you know that you can solve a problem by using numerical integrators, you can do some form of like parametric learning and then incorporate that to your architecture. I'm gonna go into one specific example of that at the end of my talk if I have time. But what symmetries do we care about? And I'm just going to describe, we care about many symmetries, but I'm just going to describe a few. We're going to describe systems that satisfy orthogonal symmetries or symmetries with respect to the orthogonal group, or maybe rotations and translations, maybe a little bit about permutations. And also, I also will describe what I describe in the title of my talk and in my abstract, symmetries that have to do with like rescaling and units, units transformations. So for instance, if my physical system is composed by objects that have kilograms, I don't know, masses and lengths or whatever. So everything has units like kilograms, meters, and whatever. So what we would want to do is to learn, if you want to do machine learning on that, then the machine learning should be consistent to unit transformations. And that you can think of it as being equivariant with respect to a group of scalings, which is not compact. And I think there's a lot of interesting math there because the group is not compact, so the things are not very straightforward. So there's many open problems in that space. Just so as a toy, I wanted to show you why am I using this equivariant formulation. And so imagine that you have like these particle simulations where every point has a position and a momentum. So this is the position, this is the momentum. And then I want to learn the dynamics of this system. So I want to predict how these particles are going to move with time. So if I constrained my learning so that if I do a rotation to the input, then the rotation of the predictions rotate accordingly, then that's something that the system will do. So it's like a reasonable constraint. And then you can quantify how much smaller is your learning space, and that will translate into improvements in generalization errors just by restricting the class of functions to a smaller class of functions that satisfy the right inductive bias for your problem. Basically, that's it. So the hard part is that you need to constrain your learning to something that satisfies these symmetries. And in this case, we'll see that it's easy, but in some cases, it could be a little bit more complicated. So how do people implement symmetries in practice in machine learning? I think the most common way to do it is through data augmentation. So you just add extra training points. Like if you know that this is a cat, then you can add different modifications of your training points that satisfy, say, the symmetries, and then you add them to your training. So something that I had in a slide, but I didn't mention, is that local symmetries, continuous symmetries, correspond to conserved quantities. So you can think if there's a conserved quantity like the conservation of angular momentum, you can make a penalization in your learning process so that you promote the conservation of that quantity. But the way we are going to do it, and the way I'm going to describe in this talk is how can you constrain the class of functions? So how can you do a parameterization of the class of functions that satisfy those constraints? And there's many ways to do it. So in particular, we care about exact symmetries. So one way to constrain the class of functions so that it satisfies the symmetries is by using something like group convolutional networks. Like that's something that from a paper in 2019 by Taco Cohen and Max Welling. There's also the idea of using message passing, like what I show you in the graph neural networks. There's also ideas regarding using irreducible representations to parameterize the space of linear equivariant functions. You can use symmetries and constraints, etc. There are many ways to do it. I'm just going to show how to use like classical invariant theory results to do it in a specific case. But I'm going to give you an overview of how people do it in practice. So basically, why do we want to do it? We want to do it because we constrain the class of functions gives you this better inductive bias, which is like we're constraining the learning to the functions that actually are feasible for my problem. And then you can derive from that generalization improvements, and like you need fewer number of samples in order to do this learning. And the disadvantage of this approach is that enforcing the symmetries can be hard, and there's a trade-off between expressivity and complexity. So what do I mean with that? I mean that if you want to parameterize all the functions that satisfy a certain symmetry, it may be that the number of parameters that you need grows exponentially, and or you can maybe parameterize a class of functions that is not very expressive. And this is something that has been noticed before in the case of graph neural networks. So in particular, this message passing approach that I told you at the beginning, it has been shown by Xu and Morris independently in two papers in 2019 that came up at the same time, that this message passing neural networks that I just told you about were just neighbors, like every node sends messages to their neighbors, cannot distinguish very simple graphs that are similar. What do I mean with that? That are different, sorry. What do I mean with that? So imagine you have this graph and there's no node features or anything. It's just like this graph given by this adjacency matrix and then this other graph. So every message passing neural network that you can write just using this vanilla message passing that I described will satisfy that for all choices of parameters, f of a is going to be equal to f of b. So there's no element in that class of functions that can distinguish these two simple examples. So that tells you that that's definitely a not very expressive model, and maybe you shouldn't use it. Or actually, there are many ways to build more sophisticated models that would not have that issue. But if you just do the vanilla implementation, you will have that issue. And so something that we did for NeurIPS 2019 was to characterize this expressive power of different graph neural networks based on their ability to distinguish the non-isomorphic graphs. So just compare. We decided that, like, say, this one was less expressive than this one by showing that every pair of graphs that can be distinguished by this model can also be distinguished by this model. And sometimes you can make the inclusion strict by showing that there's a pair of graphs that cannot be distinguished by this model, but they can be distinguished by this model. That's so there's a lot of work in the space of characterizing the expressivity of different classes of graph neural networks, because this graph neural network symmetry is the symmetry of the graph isomorphism problem, and we don't expect to be able to solve it very easily. So that's why that's the case. And then later on, we extended it to show that these graph neural networks cannot count, like many of these graph neural networks cannot be used to count substructures. So there's no graph neural network that of a certain type that given a graph, it outputs the number of, say, triangles, because because there's graphs with different sizes of triangle, different numbers of triangles that would need to satisfy that f of a is equal to f of b because of this graph isomorphism. So for instance, these two things have different number of triangles, and every message passing, a neural network will have that they are the same value. Anyway, so that's kind of like showing that implementing the symmetries may not be that easy. So you can have a nice class of functions that you use and it's easy to implement and it's easy to optimize, but in practice, it may not be very expressive. So one goal is to have a universal class of functions that is also equivariant, but that's hard, and it could take a lot of computational power. And so how one can do it in general for general groups, there's this approach that I think is very interesting, this equivariant architectures approach. There's a paper by Risi Condor and a paper by Maron in 2019, where they basically consider this model. They say, okay, a neural network, you can think of it as a composition of linear layers with nonlinear activation functions, right? And so what we can say is, okay, now we want this neural network to be equivariant. So maybe we can restrict the linear layers to be equivariant, and then we see what we should ask to the nonlinear activation function so that the equivariance is not broken by that. So, so then what people do are, what Condor and Maron suggested was to first, if you just look at the linear functions that are equivariant, typically there are not that many. For instance, if you look at rotations, there's no linear function that is equivariant with respect to rotations, or like invariant with respect to rotations. So then this is not going to be enough. So what you should do, or what they suggest you should do, is instead of looking at linear functions just from your input to your output, then you can take like a tensor product of your input space and then a tensor product of your output space, and then you can find the equivariant linear functions that go from the tensorization of your spaces. And so basically, you extend the action of your group to a tensor of inputs, a tensor product of inputs, as you would expect. You act in each of the coordinates and then you take the tensorization. And then and then you parameterize those linear equivariant functions. And those are kind of like polynomial functions, and there's more of them. So the question is, how do you parameterize these linear equivariant functions with respect to this action? And so one paper from 2021 that I thought was very interesting is this paper by Finzi, that what they propose is, okay, the space of linear equivariant functions is a linear space. So maybe I can just like sample random vectors and then random group elements, and then write the linear constraint that is the linear constraint corresponding corresponding to the equivariance of that object with respect to that group element. And then if you have enough independent linear equations, then you can just solve this large system of equations and then get a parametrization of your linear space of functions in that way. So that is kind of like a weird thing that may take a long time to compute, but if you only have to do it once, then that gives you the parameterization of your network, and then you can just like use that parameterization for training and for tests and for everything. So if you think that that's a task that if that's a network that you would use many times, you can just afford to do it just once and then give a parameterization like that. I don't know how good the parameterization is, but they have a software package that does it. This is called EMLP, and I have a student that did all the experiments for the paper that I'm presenting later in this talk, and the software package was very nice, and she could extend it, and yeah, it's great. So yeah, I recommend it. So another approach is to use the irreducible representations of the group of these spaces with respect to that group action in order to parameterize the linear equivariant maps. So the idea is that the linear equivariant maps are in correspondence with the maps between the representations of these spaces. And so if you have that this is your input, then you look at the representations of that input space and then of the output space, and then you take the representations and you decompose it in irreducible representations. And if you have the decomposition in irreducible representations, then the maps between two irreducible representations are either like 0 or a multiple of the identity. So having the irreducible representations of those spaces would give you a very easy way to parameterize the maps between them, and then the linear equivariant maps through this correspondence. So the hardest part of this approach is to write the decomposition of your representation in irreducibles, in particular of this tensor, the action with respect to this tensor. And in order to do that, people use these Clebsch-Gordon coefficients, which are sometimes hard to compute for general groups. There's a couple of implementations that I haven't used, one by Fuchs and one by Thomas. These are the first authors of these papers, where they implemented for SO3. And there's some proofs that say that this approach universally approximates all SO3 equivariant functions if you're allowed to use arbitrary high order of tensors. So it's kind of like a hierarchy. Like you can think of if you do like the higher order of the tensors that you have more expressive classes of functions, something like that. Okay. How are we going so far? Or any comments, questions, anything? Okay, great. So what I did for this paper in NeurIPS in 2021 was we took a different approach to parameterizing the space of invariant functions or equivariant functions. We used like classical results from invariant theory to give a simple parameterization instead in terms of the invariance of the group. The idea is that, so our goal was to find a way to parameterize all these functions. And so what we say is we consider our function is going to be our first function is going to be a function that takes n vectors in Rd and outputs a scalar. This function is invariant, meaning that if you act by, say, a rotation, if you rotate all your inputs, then the function doesn't change. And then we also consider functions that output a vector and they're equivariant. So if you rotate all your inputs, then your output rotates in the same way. And we consider the groups that are relevant for these physics problems. So for instance, the orthogonal group, rotations, translations, Euclidean group, which is translations and rotations, the Lorentz group, which is it's kind of like the orthogonal group, but with respect to a different inner product that is not positive definite. These are the transformations that appear in special relativity. Then the Poincaré group, which is Lorentz transformations and rotations, and then some permutations. And the actions are the actions that you would expect. So the first thing that we observe is a classical result from Weil that says that a function from RD to the n to R is OD invariant, if and only if you can write it as a function of the pairwise inner products of your vectors. So that's very simple to see. One way of seeing it is like if you're given the inner products of your vectors, then you are able to reconstruct the vectors up to orthogonal transformations using, for instance, the Cholesky decomposition. And from the physics point of view, this can be seen as like all scalars can be written in Einstein summation notation, which is like contraction of vectors. And the same thing is true for the Lorentz group, but replacing the inner product by the Minkowski inner product. So that's kind of like a simple thing that is well known. So some connection that maybe this community is interested in is the connection of this parametrization with the matrix completion literature, because, okay, so here we started from a function that take n vectors in Rd, so n times d parameters, and now we rewrite it as a function of like all the inner products, so it's like n squared. But actually, if you restrict to observe like a subset of the inner products, like the ones that I have in this matrix, then the reconstruction is unique. That's something that appears in this rigidity theory of Gram matrices that Amit Singer worked on many years ago. And it's also connected with the fact that you can reconstruct a matrix using like of and d plus one entries by using the, I don't know, semi-definite programming. So you don't need all the scalars. You could get away with like a subset of the scalars here. And presumably the error rates would be dependent on what subsets of the scalars you have observed, assuming that there's noise. And so that could be an interesting question to study. I haven't gone to it. Then we have the parameterization of the scalar invariant functions, and now we can use that to parameterize all the equivariant vector functions, which what we do is we observe that a function is OD equivariant if and only if it can be written as a linear combination of your input vectors, where the coefficient functions are scalar invariant functions, so functions of the pairwise inner products. This is a very simple thing to show for OD, because we can show that actually it's very easy to see that the function, if the function is equivariant, then it needs to be it needs to lie on the span of the inputs. If it's not OD, like if it's SOD, you will have more terms in this expression because not every function can be written. Not every equivariant function can be written as something in the span of the inputs. But in this case, that happens. And you can show that if this function is a polynomial, then these coefficient functions need to be polynomials. So this suggests the following approach to doing the learning. So given some inputs, B1 to Bn, we can construct the scalars and the pairwise inner products, and they'll learn F1 through Fn, these functions, scalar functions, So the functions of the inner products can be anything. So if it's a function of the inner products, it's going to be invariant. And if it's invariant, it's a function of the inner products. So the functions of the inner products are not constrained. So then that makes this learning part very easy, because you just need to learn like n functions of n square inputs, or less if you do the subsampling idea. And then the output is going to be a combination of that. And that gives you like this universal approach to parameterize all the functions that are equivariant with respect to rotations. And I would argue that it's easier than doing the irreducible representations. And also it's like very well, and it's very simple. So same thing can be like, okay, you can also include translation invariance or equivariance in an easy way by just say subtracting the center of mass of your objects. And if you wanted to do equivariant, you can just construct these features based on the subtraction of the center of mass and then add it in the end. And there's also a way to extend this to permutation invariant functions in a way that looks like message passing. Maybe I'm not going to explain the details because I'm a little slow, but it's fine. And so an interesting question is like, okay, what we did for the orthogonal group, is that something that is, I guess, like, is that something that can be more general, can be done for more general groups? And there's yes, and we can use invariant theory to see how to do this in a general way for any groups. The idea, or like not for any groups, but for reductive groups, which are all the groups that I know. So the idea is the following. If G is a reductive group, then the algebra of invariant polynomials has the property that is called like that is known as like Cohen-Macaulay, that basically is that you have two sets of generators, the primary invariants and the secondary invariants, and every element in your algebra can be written as like a very nice combination of these invariants. So it's like it's a polynomial function of your secondary invariants, where the polynomial coefficients are polynomials of your primary invariants. So this is like the general characterization of the algebra of invariant polynomials. And the question is, okay, in particular, what I show you just now for OD is just saying that the scalar products are the primary invariants for this algebra, and the secondary invariants are trivial. That's it. But for more general groups, or in particular, for instance, if we are looking at the graph neural network, so if we're looking at the invariance with respect to permutations by conjugation, I believe that is not fully characterized, the invariant polynomials and the secondary, the primary invariants and the secondary invariants for like weird actions, like that action by conjugations and things like that. And the thing is that it could happen that the number of invariants grows is like exponentially large on n, and then that would make it so that this approach is useless. So the fact that this approach is useful is because we ended up with like a very nice set of invariants that was small enough to use it as a parameterization for neural networks. So yeah, so this is work with Ben Bloom-Smith, who is going to join Hopkins as a postdoc in a few months, and he did his PhD in invariant theory, so he does all this. Yeah, he's very good at teaching. Anyway, so As an example, let me show you the example of this dynamical system, which is this double pendulum with springs. So the data is just like the positions and momentums of these two masses, and we can compute the kinetic energy of the system and the potential energy of the system, and the Hamiltonian, which is the sum of these energies, is a conserved quantity. And we can, and the goal is to predict the dynamical system. So if we assume that the gravity is an input vector, then we can see that this dynamical system is equivariant with respect to all three. Because if I rotate the positions of the masses, like in this direction, it's obvious that the system is equivariant. But if I rotate it in that direction, it may not be equivariant, right? But if you rotate the gravity as well, then it's equivariant. So that's basically what I'm saying here. So if you have the gravity as an input, and then you can compute the inner product of the gravity vector with all your vectors in order to construct all these features, then that would give it to you. And so the way we learn this dynamical system is by using this Hamiltonian neural network, which basically what you do is you learn a Hamiltonian from the data, and then you use a Hamiltonian integrator to do the predictions, and then your loss function is with respect to the predictions done by this Hamiltonian integrator of your data. So you learn a parameterization of the Hamiltonian, and then you use a Hamiltonian integrator in your learning end to end. And so that's one of the ideas of this like physics-inspired machine learning, where you incorporate knowledge of your physics models in these machine learning processes. Just like you don't just try to learn the trajectories with a neural network without like incorporating the physics of the problem to it. Anyway, we show that it works pretty well, and we compare with EMLP. They didn't do the O3 equivariance in this EMLP paper, but they did the same simulation with this double pendulum, and that's where we took a lot of the code from them, and it was very nice just to have a baseline to compare against. And we did very well with these scalars-based methods. This EMLP is the one that learns the constraints on the fly, and they parameterize these linear layers with nonlinear activation function, and these linear layers are learned with this method that I just told you about. So that's it. This is another numerical example. So in the 3 minutes that I have left, I want to tell you a little bit of like how to quantify how much do you gain by imposing these symmetries. So there is this paper by Lesedi and Sadie in 21, where they look at the following. They look at data sampled from a distribution in RD, and then this group acting in RD, a compact group, and then the data is sampled from the distribution, which is actually invariant, right? Sorry, I should have said that earlier. And so say that your training data is given by xi's and yi's, where the yi's are generated as some f star of xi plus some noise, where f star is an invariant target function that you don't have access to. But you know that what you want to learn is given by some invariant target function with respect to G. So what they show is that if you define the risk of the function as the expected value of the error in your test set, or like the expected value of the error in the data space, then they show that the generalization gap is actually the norm of the generalization gap for, so what is the generalization gap? Sorry. If f is a function, and you can consider the risk of f, and then you can consider f bar, which is the projection of f onto the space of invariant functions, right? And the generalization gap is how much do you gain by imposing the symmetries, which is the risk of F minus the risk of the projection of F onto the space of invariant functions. And there's a simple computation that actually shows that this is the norm of the orthogonal, the projection of F onto the orthogonal complement of the invariant space. That's the expected thing that you gain. So basically it's something about you counting dimensions, counting how many fewer parameters you have when you parameterize the space of invariant functions versus parameterizing everything. So that tells you that you always gain something, like even if you do the regression in a non-invariant space and then you project it onto the space of invariant functions, you always gain something. And that something is the norm of the function projected onto the orthogonal complement of the space of invariant functions. And the norm is with respect to the data distribution, which needs to be invariant. And maybe this is a little bit technical, but I'm happy to discuss if you're interested. And so, but this is for compact groups. What we've been working on is to see what happens in non-compact groups, and we are writing a paper. We haven't finished it, but we are very close. What we say is, okay, if we look at specific groups that are given by these units conversions that I told you at the beginning. So say that our double pendulum before had this potential energy and this kinetic energy, and this is given by an energy. Actually, it's an energy, has units, and the units is kilograms meter squares time divided by second square. So if I do a conversion of my units, and instead of giving your masses in kilograms, I give them in pounds, then the predictions should be transformating accordingly to that. And so how can we parameterize the space of functions that do that? Well, there's a very classical theory, very old theory that is called dimensional analysis, that has the main result. This is Buckingham Pi theorem that tells you that if you have a function with inputs in RD that each one has units, then you can do a transformation of your inputs to a dimensionless feature space. And then any function that is equivariant, unit equivariant, or equivariant with respect to rescalings, can be expressed as a function of these dimensionless features. So the natural architecture to use is you take your input features that have units, then you construct these dimensionless features, then you learn a neural net that produces some dimensionless labels, and then you do a rescaling to some dimensional output. And we actually have some numerical examples in this. Is the same double pendulum that I showed you before. And we see that actually in the baseline experiments, we don't perform as well. And the reason why we don't perform as well as before with just the scalars is because these dimensionless features require to divide by your inputs. So you have mass 1, and then you have mass 2, and then a dimensionless feature could be M1 divided by M2. In order to construct these dimensionless features, you need to divide, like, I don't know, lengths and masses and things, so that everything cancels out their units. And that makes it very numerically unstable. So we have to do some things to stabilize it. And in the end, the learning is not as clean as in the previous formulation that we had. However, the generalization is very nice. Like this model generalizes to other settings much better than the previous one. For instance, if we take everything that has units of kilograms and multiply it by 5, then the learning shouldn't change. And this is the experiment too. Like, well, the loss function is not invariant in this case, so the loss function is not the same, but the performance is the same. However, if you do that to the baseline, which is our own implementation from the units paper, you see that the error, like if you multiply everything that has units by 5, you are kind of like in an out of distribution setting, and your learning doesn't work. And this experiment 3, we did something that was out of distribution for both the baseline and the dimensionless, where like we sampled, we did the training set sampled from one distribution, and the test set sampled from a different distribution, and then we look at how the error changed to that distribution. So that's I think this is everything that I wanted to say. I think that enforcing exact symmetries in machine learning is the right thing to do, and there's interesting math problems regarding that. I talked about graph neural networks, which are equivariant with respect to the action of permutations by conjugation. And there is something, some interesting direction, which is the characterization of the expressive power of these graph neural networks via the graph isomorphism problem that I told you earlier. Then we also discussed the symmetries in classical physics, providing a simple characterization of all equivariant functions with respect to physically relevant group actions. And that is universal, and it doesn't really require you to go to very high order tensors. Like there's no, it just is, you don't have to do that. So that makes it easier. And last things, yeah, there's some open problems. Something that I care about is like try to use this multi-scale information from these like fast multiple methods into the implementation of these like of these models. I haven't done it, and it could be a little complicated, but I think it's an interesting question. And then the generalization bounds and extension to general groups, explore connections with matrix completion, and also I'm interested in maybe designing a subset of permutation invariant scalars that are universally and expressive. And there's some application domains apart from the physics one that I described. And this is my references, and thank you for your attention.
All right, thanks, Soledad. I'm gonna react with this icon here. I encourage everyone to smash that. And yeah, any questions?